Hi everyone, and welcome in this new episode of Math Puzzle with Q. In today's video, we are going to analyze an interesting functional equation. So the way we define this functional equation is the following. So we do the integral from x minus y to x plus y of f of t dt. This should be equal to fx multiplied by fy. So what we're going to do is to identify what kind of property this kind of function should verify, and also what are all the functions that can satisfy this equation. So one assumption that we have is that the function f is defined from R to R, so the set of the real number to the set of the real number. And we also assume that f is continuous. We are going to show that f is infinitely differentiable. So the way we are going to do that is by first defining a function big F, and big F is going to be defined as being equal as the integral from 0 to x of f of t dt. And so the way we can rewrite the equation is big F of x plus y minus big F of x minus y is equal to f of x multiplied by f of y. One first thing that we can notice is that the function f equals 0 verify this equation. If you have f equals 0, you have this that is equal to 0, this that is equal to 0, and the integral of f from x minus y to x plus y of 0 dt is also equal to 0. So the function f equals 0 totally satisfies this equation. What we would like to see is what kind of function f that is not always equal to 0 can verify this equation. So we are going to assume that f is different from 0, and this means that there is at least one u that belongs to the set of the real number, such as f of u is different from 0. And so thanks to that, what we can write is that fx fu is equal to big F of x plus u minus big F of x minus u. And because we know that f of u is different from 0, we can write that f of x is equal to 1 divided by f of u of big F of x plus u minus big F of x minus u. And the thing is that f is the integral of a function that is c0, so continuous. So big F is c1, and this big F also here is c1. So at the end we have the function f that is also c1. So not only we can differentiate this function, but also the derivative of f is continuous. And thanks to that, we can demonstrate by induction that f is actually C infinite. Thanks to that, we know that we can differentiate f as many times as we want. So we are going to write the equation here again. So f of x plus y, I should say big F of x plus y minus big F of x minus y is equal to f of x multiplied by f of y. So on one hand, we are going to differentiate this equation by x, and on the other hand, we are going to differentiate by dy, by y. So here, what we have is f of x plus y minus f of x minus y is equal to f prime of x multiplied by f of y. And let's differentiate that by x one more time, and we have f prime of x plus y minus f prime of x minus y is equal to f prime prime, so the second order derivative of x, fy. When we differentiate by y, what we obtain is that fx plus y plus f of x minus y. So the reason why we have a plus here is that it's because of the minus y that we can see here. So the minus become plus. And this is equal to f of x, f prime of y. Let's differentiate again by y. And we have f prime of x plus y minus f prime of x minus y. So again, because of the minus here, we obtain a minus after differentiating, is equal to fx f double prime of y. And what you can notice is that this part is the same as this part. These two things are completely equal. So we can write that f prime prime of x, fy, is equal to f of x, f prime prime or f second of y. And this equation is valid for any x or y. And so in particular, this equation is valid if we replace y by the number u, for which we know that f of u is different from 0. So we can write that f second of x fu is equal to f second of u fx, or we can rewrite that as the second order derivative of x is equal to the second order derivative of f in u divided by f of u multiplied by f of x. And we're going to use this equation in a moment, and I know that many of you may recognize this very well-known differential equation that is second order derivative of y plus c of y equals 0. So we are going to use what we know about this differential equation, but before that we are going to keep discovering some interesting property about f before we solve this equation. The first thing we're going to try to discover about f is if it has some features, such as if it's an odd or if it's an even function. And also if we can identify some particular value of f in some specific number, or some specific value of the derivative of f in some specific number. So about the question whether f is an odd or even function, the way we are going to answer this question is to write that big F of x plus y minus the big F of x minus y. As we know, this is equal to f of x multiplied by f of y. And what we can notice is that if we reverse these two elements, we may find something interesting about f. So let's say that this is equal to the opposite of f of x minus y minus f of x plus y. So big F, of course. In that case, what we can see is that we have the equation, the same equation as above, but in which we have replaced y by minus y. So this is equal to minus of f of x, f of minus y. So we just prove that fx, fy is equal to minus fx, f minus y. And this is valid for any x or y. So in particular, this is valid for f of u, which is different from 0. And we can write that fu, fy is equal to minus fu f minus y, or in other words, that fu multiplied by fy plus f minus y is equal to 0. And since we assume that fu is different from 0, we obtain fy is equal to minus f minus fy. So this proves that the function is actually an odd function, and in particular, for any odd function, we have the property that f of 0 is equal to 0. Now let's use one of the derivative of the equation that we used before, so for example that one, and we are going to derive a property about the derivative of f in 0. So we have f of x plus y minus f of x minus y that is equal to the derivative of f in x multiplied by fy. So if we replace x by the number 0, we have f of y minus f of minus y is equal to f prime of 0 multiplied by fy. And because the function f is odd, as we have seen before, we know that f of minus y is equal to minus f of y. So we can write 2f of y is equal to f prime of 0 f of y. And this equation is valid for any number y. So in particular, this is valid in the number u, for which we know that fu is different from 0. So we can write fu multiplied by 2 minus f prime of 0 is equal to 0. And again, because fu is different from 0, we can write that f prime of 0 is equal to 2. So now let's go back to the important equation that we found before, which is this differential equation here. And we are going to identify what can be the function f depending on the value of f second of u divided by f of u. So let's start with the case 1, where f second of u divided by f of u is equal to 0. So in that case, it means that for any number x, the second order derivative of x is equal to 0. So that implies that f of x is equal to ax plus b, and we are going to identify what should be the value of a and b. So because f is an odd function, as we have seen above, this means that f of 0 is equal to 0, but of f of 0 is equal to b, that is equal to 0, and on top of that, we also know that f prime of 0, which is equal to a, must be equal to 2. So considering all of that, we can write that f of x is exactly equal to 2x, and we can check that to see if it actually works. So let's take the integral from x minus y to x plus y of 2t dt. This is equal to t squared from x minus y to x plus y. So this is equal to x plus y square minus x minus y square. And you can easily simplify that by using the fact that this is equal to x squared plus y squared plus 2xy. Here you would have x squared plus y squared minus 2xy, and at the end you will obtain 2xy plus 2xy, which is equal to 4xy. And we notice that this is also equal to 2x multiplied by 2y, which is fx, fy. So indeed, the function fx is equal to 2x works for that equation. So now let's go to a more interesting case, which is the case where f second of u divided by f of u is strictly positive. So we are going to call this number omega square. So we write that omega square is equal to the second order derivative of f in u divided by fu. And we can write that the second order derivative of f is equal to omega square of f. We perfectly know how to solve this kind of equation, and the solution of this type of equation are all the f of x that are equal to big A multiplied by the cosine hyperbolic of omega x plus big B multiplied by the sine hyperbolic of omega x. And one thing that we can use is that because f of 0 is equal to 0, this implies that the big A is equal to 0. This is because when you replace that by 0, you will have A cosine hyperbolic of 0 plus B sine hyperbolic of 0. So this will disappear. This is equal to 1. And this is equal to big A, and this needs to be equal to 0. So you can deduce that A is equal to 0. Another thing is that because we have f prime of 0 is equal to 2, this implies that B, when you differentiate the sine hyperbolic, you have a cosine hyperbolic. So b cosine hyperbolic of 0, because we differentiate it and you have omega x inside, you can write that omega b cosine hyperbolic is equal to 2. Cosine hyperbolic is equal to 1. So this implies that omega b is equal to 2. And this implies that b is equal to 2 divided by omega. So at the end, the only function that can work is actually the function f of x is equal to 2 divided by omega of sine hyperbolic of omega x. Now let's talk about the case 3. So for the case 3, what we have is that the second order derivative of f of u divided by f u is strictly negative. And in that case, we are going to write that omega square is equal to minus second order derivative of u divided by f of u. And we can write that the second order derivative of f plus omega square f is equal to 0. We also know how to solve this kind of equation, and all the functions that verify this differential equation are the function f of x is equal to a cosine omega x plus b sine omega x. And similarly to what we have done before, we can write that f of 0 equal to 0 imply that a is equal to 0, and f prime of 0 is equal to 0 imply that b omega is equal to, f prime of 0 is equal to 2, imply that b omega is equal to 2, and that implies that all the functions that can verify this are f of x is equal to 2 divided by omega of sine of omega x. So at the end, we have finally found all the functions that can verify the equation integral from x minus y to x plus y of f of t dt is equal to f of x, f of y. And all the functions that verify this equation are all the f that are either the function that is 0 everywhere, or we have also all the function, we have x that is transformed into 2x, but we have also x that transform into 2 divided by omega of sine hyperbolic of omega x, and that's for all omega that are strictly positive. But we have also all the x that are transformed into 2 divided by omega of sine omega x for all omega that are strictly positive. And that's all the solution of the functional equation described above. And that's all for today.